everyone. I welcome you all to this digital classroom for the subject control systems. In the previous lecture, we discussed about rule number 6 and 7 for the construction of root locus. And today, we are going to discuss about rule number 8 to calculate the angle of departure and angle of arrival. Here, rule number 8 is subjected to calculate for the angle of departure as well as angle of arrival. And this rule is applicable for complex conjugate pole or complex conjugate zero. That is, for a given open loop transfer function, if we have any complex conjugate poles or complex conjugate zeros, then this rule becomes applicable. In this rule number 8, we have two categories, that is, angle of departure calculation at complex conjugate poles and angle of arrival calculation for complex conjugate zeros. First, let us discuss about angle of departure at complex poles. As branches leaves from open loop poles, it is advantageous to know at what angle it departs from the complex conjugate pole. And this angle at which it departs from the complex pole is called as angle of departure, and it is denoted by phi d, where phi d is given by 180 degree minus phi, and phi will be equal to summation phi p minus summation phi z, where summation phi p is given by the contribution by the angles made by the remaining open loop poles at the pole at which phi d is to be calculated, as well as summation phi z is given by contribution by the angles made by the open loop zeros at the pole at which phi d to be calculated. Similarly, angle of arrival is given by phi a equal to 180 degree plus phi, where phi is equal to summation phi p minus summation phi z. And angle of arrival is subjected to complex zeros. Let us take an example with complex conjugate pole here in this case. And we know that all the branches which is leaving from the open loop poles, all the branches will be leaving the open loop branch. With respect to rule number 2, we know that all the branches will be leaving from open loop poles and it will be terminating at open loop zeros. So it is more important to know the angle of departure of the complex pole. That's the reason why we call it as angle of departure when it is subjected to complex pole. And with respect to same rule number, it is very clear and evident that the branches will be arriving at open loop zeros when k tends to infinity. So let me take another example. Complex conjugate is 0. Again, it's a combination of real as well as imaginary, a complex conjugate pair which we get here. And with respect to rule number 2, it is very clear that when k is equal to 0, it starts from an open loop pole, and when k is equal to infinity, it terminates at a open loop 0. So with respect to a complex conjugate pole, it is very advantageous and important to calculate for the angle of arrival when it is subjected to a complex conjugate 0. And that is the reason why if it is a complex conjugate pole, we calculate for angle of departure, and if it is a complex conjugate 0, we calculate for angle of arrival. It comes from rule number 2. The notation for angle of departure is phi d and angle of arrival is represented by phi a. Let me take an example and justify this rule. In this example, you have been given with 4 poles at s is equal to 0, comma, minus 3, and we have a complex conjugate pair at minus 1.5 plus 3j as well as at minus 1.5 minus 3j. As in this example, you are given with a complex conjugate pole, we are supposed to calculate the angle of a departure for this complex conjugate poles. We know the formula to calculate the angle of departure, which is given by phi d equal to 180 degree minus phi. And to calculate this, we have to first join all the remaining poles to the complex conjugate pole which is under consideration. Let us assume that we are going to calculate the angle of departure subjected to this pole, that is minus 1.5 plus 3j. Then, as I told you now, we have to join all the remaining poles to the complex pole under consideration. So we have rest of the 3 poles, one at minus 3, one at 0, and the other at minus 1.5 minus 3j. Now we have to join all the remaining poles towards the complex pole which is under consideration. So let us join it with dotted lines. This is the first step. Now we have to calculate the angle subtended by phasors joining the poles to pole under consideration. So we have to calculate the angle of contribution for the pole at s is equal to 0 and the angle of contribution for the pole at s is equal to minus 1.5 minus 3j as well as the angle of contribution for the pole at s is equal to minus 3. That gives you summation phi p. The sum of all the angle contributed by the rest of the 3 poles gives you summation phi p. Similarly, join all zeros to pole under consideration and adding all the angles will give you summation phi z. If you have a 0 in this location, then we have to join all the zeros and then again you have to calculate its contribution by calculating its angle towards the pole which is under consideration. As we don't have any 0 in this example, this term becomes 0. Now let us calculate the angle of contribution by the rest of the poles one by one. So for angle of departure which is subjected to minus 1.5 plus 3j, now we are going to calculate for the angle contribution of the angle at the pole s is equal to 0 and I have represented it as phi p1. To calculate the angle phi p1, we can consider the complete angle. This gives you 180 degree minus x gives you phi p1, where x is this angle exactly. So let me highlight with a green color exactly this region. So opposite side is 3 and the adjacent side is 1.5. Hence we get phi p1 is equal to 180 degree minus x, where x is given by tan inverse of opposite side is 3 and the adjacent side we had 1.5. So I have written here as 180 degree minus tan inverse of 3 by 1.5. So we get 116.56 degree. This is the angle of contribution by the pole at s is equal to 0 towards the complex conjugate pole which you are going to calculate for angle of departure. Similarly, let us calculate for phi p1, that is the contribution for the other pair of the complex conjugate, that is minus 1 minus 3j. So it is very clear that this angle will be exactly equal to 90 degree. So I can write it as phi P2 equals to 90 degree. Now our point of interest is to calculate for phi P3, which has been represented here, that is subjected to the pole at s is equal to -3 towards the point of interest. To calculate phi P3, let me take this right angle triangle. So this is 3 and this adjacent side is again 1.5. Hence we can write it as phi P3, which is given by 3 by 1.5. This is exactly at 1.5. So this length will be equal to 1.5. So it has been written here as tan inverse of opposite side by adjacent side. 3 divided by 1.5 exactly. Hence phi P3 is given by 63.43 degree. Now we have to sum up phi P1 plus phi P2 plus phi P3. We get summation phi P. As we don't have any zeros here, this contribution is 0 in this case. So after substituting for phi P1 plus phi P2 plus phi P3, we get the summation phi P is equal to 270 and summation phi Z is equal to 0 degree. Hence phi is equal to summation phi P minus phi Z, that is 270 degree. Now we have to substitute for 270 degree in this equation. Hence phi D will be equal to 180 degree minus phi, where phi is 270 degree. I have substituted 270. So 180 minus 270, I get minus 90 degree at minus 1.5 plus 3j. So which is subjected to this complex conjugate pole at minus 1.5 plus 3j. Now it is very clear that the angle of departure for this pole minus 1.5 plus 3j is exactly at minus 90 degree. This angle is 0 degree, this is 90, this is 270. If you move in the anti-clockwise direction, if you move in the clockwise direction, we get 0 degree minus 90 degree. Hence minus 90 degree can be located exactly at this angle. So this gives you the angle of departure subjected to complex pole at minus 1.5 plus 3j minus 90 degree. Similarly, if you calculate for the other pole at minus 1.5 minus 3j, we know that as the root locus is always symmetric with respect to the real axis, you can say that the other side we get an angle of plus 90 degree at minus 1.5 minus 3j. And this is the procedure to calculate the angle of departure for a given complex conjugate pole. And exactly at an angle of ID minus 90 degree, the pole starts moving. This shows the moment of the pole with respect to the increase in value of k. Similarly, on the other side, as the angle of departure for this pole is exactly at plus 90 degree, the pole starts moving in this direction. Hope you have understood with these concepts of the calculation related to angle of departure. Now, let us look into the steps involved in root locus. Step 1. Get the general information about number of open loop poles, zeros, and number of branches from G of S, H of S. From the given data, we have to get some of the general information like how many number of open loop poles we have, how many number of open loop zeros we have, and the total number of branches. General information. And moving on to step number 2, We have to draw the pole zero plot and you have to identify the sections of real axis for the existence of root locus. This is the place at which we have to check for the existence of root locus. And then we have to predict the minimum number of breakaway points by using the general prediction method. Moving on to step number 3, we have to calculate the angle of asymptotes. We have a formula to calculate the angle of asymptotes. Making use of the formula, we have to calculate. That is step 3. Moving on to step number 4, we have to calculate for centroid and we have to make use of step 3 and step 4 and we have to plot it in the S-plane. Moving on to step 5, it is subjected to the calculation of breakaway and break-in point. If breakaway points are complex conjugate, then we have to use angle condition to check for them for their validity of breakaway point. So if any problems if we solve subjected to a complex conjugate pole and while you are calculating for breakaway point, you will clearly understand the meaning of this step exactly. And you know the procedure to use the angle condition as well as magnitude condition whenever there is a necessity. We know the procedure to calculate the breakaway and break-in point. We have to write the characteristic equation 1 plus g of s into h of s equal to 0. Then we have to represent k and the s polynomial on the other side. Then differentiate k by s, dk by ds equated to 0. Based upon the highest power of s, we get the number of roots. If the highest power is 2, we get 2 roots. If the highest power of is 3, you get 3 roots and so on. And based upon that, we have to check for the validity and its existence. Moving on to step number 6, we have to calculate the intersection point of root locus with imaginary axis. We have a procedure. We have to make use of route array. The first step is to write the characteristic equation 1 plus g of s into h of s is equal to 0. Then we have to formulate the route array. And after generating the route array, we have to calculate the range of k, which determines the stability of the system. And exactly we have to find k margin, which makes the system to be as marginally stable. And we have to calculate the roots on the imaginary axis. If k margin is positive, then the root locus intersect on the imaginary axis. And if k margin is negative, then the root locus does not intersect with the imaginary axis. And the root locus will be lying totally on the left half of the S-plane if k margin is negative. Make a note of it. I will repeat you once again. If k margin is positive, root locus intersect with the imaginary axis and you will be getting a root on the imaginary axis which makes the system to be as marginally stable. But if k margin is negative, then the root locus does not intersect with the imaginary axis, which means that the total root locus lies on the left half of the S-plane, which means that the system is stable. Moving on to step number 7, calculate the angle of departure or angle of arrival if applicable. This is related to the last rule which we discussed right now, which is related to a complex conjugate pole or a zero. Step number 8, we have to combine all the steps starting from 1 to 7 and we have to plot the final sketch of the root locus. And finally, step number 9, predict the stability and the performance of the given system by using root locus. Finally, we have to speak about the stability with respect to the parameter k and we have to specify the ranges at which the system is stable and at which the system is marginally stable and at which the system is becoming unstable. So in this lecture, we have discussed about rule number 8 in detail with an example and the steps to be followed for the construction of root locus. In the next lecture, let us solve few example problems related to root locus. Thank you.